Namaskar, greetings friends, and welcome to my series of video lectures. And today I'll be starting off with a new series which is a introductory series on material science, and this is the first lecture of that series. And today we'll be talking about crystal structure, and before that a little bit about basics of material science. So over the ages of human civilization, different materials have played very important part in our growth, and right from the Stone Age through different metal ages, we reached the industrial age, and then came the plastics, then the semiconductors. So all these are jumps in technology which were driven by materials, and maybe we are heading to the nanomaterials age up next. So it is important to study material science, and this lecture series will be mostly dealing with the solids. There are many states of matter: solids, liquids, gas. Also there are plasma and other things, but we will be mostly dealing with solids. And among solids, it's well known to you, there are crystalline solids and some amorphous solids. According to bonding, there might be ionic, covalent, metallic crystals. Some molecular crystals are also possible, like naphthalene. Then there are amorphous solids, rubber, glass, gels and plastics. Sometimes we will see that glassy materials are also classified as supercooled liquid, because from a molten state the liquid is cooled down very rapidly, say silica or such glasses. So from a molten state it is cooled down, so it is like a snapshot of liquid in time, frozen in time. So that's what makes the glassy material. But our focus here is right now on the solids, and among the crystalline and amorphous materials there are certain differences. Crystalline materials have very sharp melting points. They have stronger intermolecular forces. Their physical properties are dependent on the direction within the crystal, and there are well-defined planes and cleavage planes. And amorphous materials do not show this kind of properties. So now we will speak a little bit about the materials tetrahedron. And in material science we deal with mostly these materials: ceramics, metals, polymers and their composites. So composites are combining two or more materials, different materials into one, and they have different properties. And material science is the study of the structure, the processing, the properties and the performance of these various type of materials. A quick stop about bonding. So we know that there are ionic, covalent, metallic and van der Waals bond that do exist, and we can classify different materials depending upon the contribution of the type of bonding. And here we have a very nice representation, a very peculiar tetrahedron, in which we have shown that with the help of these legends, these orange dots, they mean these are located in the front surface. For example, diamond, graphite, methane. This is for tungsten. These red dots show something in middle of the tetrahedron, and these blue ones show somewhere in the back surface. So this is for the sodium chloride, cesium fluoride and such materials. And this gives you an idea about distribution of the contribution of different type of bonding. And in a solid, one type of bonding may dominate over the others, but other contributions can also be present. So that is the whole point of showing this kind of a structure. Now we will talk about the crystal lattice, because we are living in a three-dimensional world. We have this Cartesian coordinate system. We have x, y and z axis and the angles in between them. If it is an orthogonal system, all these angles are 90 degrees, alpha, beta and gamma. If it is non-orthogonal, then they are different. So in that space, there is a geometric construction which you can think of as a blueprint for a crystal. It is like nature's blueprint for a crystal in real space, and that is called a crystal lattice. So it is a geometric construction, periodic pattern that is repeated in the space, and these are just geometric points, not really associated with some physical particle or something in as a lattice. So it is a geometric construction in space. Example, I have shown a 2D square lattice. And when this lattice gets associated with basis, which is basically, it can be an atom, it can be a number of atoms, a molecule or such things, and when lattice is associated with a basis, it becomes a crystal structure. So each lattice point gets associated with the basis, that is the unit of repetition, and these basis and lattice together make up the whole crystal. And in nature there are the 14 Bravais lattices, and among them there are certain families like the cubic, then the tetragonal, orthorhombic, monoclinic, triclinic, rhombohedral and hexagonal. And there is a further classification among themselves that they can be primitive, so there would not be any additional atoms within the volume, but only at the vertices. Base centered, also sometimes called side or end centered, so only in some particular faces, like in this case the top and the bottom or the ends, how you want to visualize, there would be additional atoms. Body center, somewhere within the body center there is the presence of another lattice point or atom in the crystal. So these kind of structures exist, and finally there is the face centered. So on each of the face there is a presence of another lattice point or atom, and these kind of structures you can classify each of them as this PCIF and associate with the family. Now interesting thing is this two are basically the same structure. This is the hexagonal, and it is just showing the primitive cell of a hexagonal lattice within the entire structure. So if we look at some of real case examples, alpha polonium is the only simple cubic crystal that exists, or the primitive cubic as you like to call. Iron sometimes shows body centered, and in one phase it is BCC, body centered cubic. In under certain temperature conditions and external factors depending upon that, it can undergo a phase transition and form FCC lattice also. This is showing an aluminium FCC. This is another copper aluminium compound. In textbooks and some web resources, and in many cases you will see that there are some more interesting structures, diamond, rock salt and such, and we had not mentioned them about in the Bravais lattice, but the fact is these are actually interpenetrating FCC lattices that give rise to this kind of beautiful structures. So zinc blende, which is also the structure of silicon, which is this diamond structure, it is actually along the body center, 1/4 along the body center. Two interpenetrating FCC lattices are there to make this diamond structure. For rock salt, it is along the sides. This is also two interpenetrating FCC lattices. NaCN is an orthorhombic crystal, primitive cell. And now let us talk about the coordinates, because to specify this kind of a lattice, any of them, you need a coordinate system, and these are the x, y and z Cartesian coordinates, and this is obviously an orthogonal system. All these angles are 90 degree, and I can represent these lattice vectors A, B and C in these three axes. So they are just like sort of a unit vector. So these are the lattice vectors that determines the lattice spacing, the spacing between two lattice points in each direction. So these vectors are there, and with that you can represent any point in the lattice, and this is a vector you can construct. In some cases the system may not be orthogonal, and you will have a situation something like this, where these angles are not 90 degree. And to define planes, because planes are very important in crystal structure, as we will go deeper into this course, we will realize that planes are very important in any crystal structure. And to specify a plane in a crystal structure, it is important to know the Miller index or the Miller indices of the plane. And how to construct that? Let's take an arbitrary example, an orbit lattice which is not orthogonal. So the way of constructing or knowing the Miller index of a particular plane is basically you consider the intercepts along the three axes. Say this is P, Q and R, and the reciprocals of this will be 1 by P, 1 by Q and 1 by R. First you take the intercepts, you know the intercepts, then you take the reciprocal, and then you normalize. So these normalized numbers H, K and L, these specify your Miller indices, and it doesn't represent only a single plane but rather a set of parallel planes, a family of planes. And the brackets are important. This kind of bracket represents the plane, and this square bracket represents a direction. So direction H scale and plane H scale are denoted like this in crystallography, and direction is basically perpendicular to the plane, so like this lattice vector. And if you observe a bar over this any of these indices or more, so the bar represents the negative intercept on that particular axis. Sometimes you will see another index in case of rhombohedral or hexagonal lattice. So this is like I equals to minus H plus K, so it will be denoted by I bar sometimes, and this is only for rhombohedral and hexagonal to identify the plane more easily in such cases. So it is just a construct, but usually you will have only these three Miller indices. So let us first discuss a little about with an example. So here I have a simple cubic crystal, and I want to find out the Miller index of this plane. So obviously the intercepts are along X. This is along the lattice vector A, you can say this is 1 for Y, and because the plane is parallel to the Z axis, the intercept will be infinite, and the reciprocals will be 1, 1, 0, and it is already in terms of integers, so you normalize, it makes no difference here, it is just 1, 1, 0. So the Miller index of this plane, this particular plane you see, will be 1, 1, 0. And coming to another example, say this this is the plane we want to understand. This is the one whose Miller index I want to calculate. So we see here it has a negative intercept in x. In the x-axis it intercepts at -1. It does not intercept y, so it has this infinity for this, and around 2/3 is the intercept at z. So now first we have to take the reciprocals, so this will be -1, 0 and 3/2, and then we go on to normalize into integers. So once we have done that, so this is -203, so the Miller index becomes 2 bar 0 3. So this plane is 2 bar 0 3. In this slide I have shown some examples. You can also study and try and calculate Miller index of different planes. So it is often a very interesting problem that you get in undergraduate material science or solid state physics, that you are given to identify the Miller index of a plane. You can obviously practice and calculate more planes, more intercepts, and sometimes negative intercepts and these things. Now to come to the concept of interplanar spacing, which will be very important because for example there are diffraction studies, and in that interplanar spacing plays a very important part for X-ray diffraction or electron diffraction studies. And so as I already said, that Miller index H scale represents not just one single plane but a family of planes, so a set of parallel planes, and they have an interplanar spacing, right? So if there are planes, a set of parallel planes, they will have a certain interplanar spacing, and that spacing, how to calculate that, this formula is there. Say I have an orthogonal lattice, all the angles are 90 degrees, and then what I get is DHKL is the spacing between a set of planes with the same Miller index HKL. So that will be given by this formula, and we can calculate, say for a cubic lattice, D001 will be A, D111 will be A by square root of 3, and so on. So these kind of examples we can do, because if you know the lattice parameter of a certain material, then you will know the interplanar spacing of that for a particular plane, and that will also help you to identify the X-ray diffraction spectrum, which plane is there, which kind of material is there, these things. And finally, just I will give in today's final slide, I'll just give you a introduction about the planar density, because we have been talking about the crystal structure and planes, and the properties in a crystal differ from one plane to the other. Or say for you have a same, you're considering a single plane but different materials, so different crystal structures are there. So in the same plane, in different materials, you will see different properties, but also in a same material in different planes you will see different properties as well. So why does that happen? To understand in a very basic, very crude manner, say for example I take a cubic crystal and take the 111 plane, like I have taken here. I have a cubic crystal 111 plane. For simple cubic, if the atoms are all touching each other, even in that case, so there will be atoms at these corners, and I'll have 3 of them, and this will be my planar density. Some part of the 1-1 plane is occupied and some part is vacuum. So obviously this one for simple cubic will be different if the case is a body centered cubic, because there will be one more atom at the body center, and then I'll have a different planar density. So you can understand if we consider hard spheres, because in crystallography we will be mostly considering atoms as hard spheres, so we use this hard sphere model. So if spheres are packed in this manner or that manner, so depending upon the plane, mechanical properties would be different, electronic properties would also be different, and many other differences would show up. Resistance, for example, of a silicon wafer. Silicon is a diamond structure, but silicon wafer in 110 and 111 direction are not the same, and that this is the kind of reason behind it, in a very crude manner. So in today's topic we have covered some very basic things about crystallography, and I would suggest you study these books, and there are many other excellent authoritative textbooks available. And thank you for your support, and I hope you like the video. Do put your comments, and like, share and subscribe the channel, share the link to your friends, and I will see you in the next video lecture, and thank you for the time.